Welcome back, focused learners, to this explainer. Today, we're going to completely demystify something that, honestly, trips up even the most seasoned senior engineers. We are going to design an end-to-end OLAP analytical data platform, completely from scratch. By the time we're done here, you're going to have the mindset of a world-class architect. You'll be ready to tackle massive data pipelines, understand super complex schemas, and, crucially, choose the exact right technology for the job.
All right, here's our agenda for today. We'll start with the core challenge, explore the great OLAP divide, master the Star Schema, build out a Medallion pipeline, select our tools, and finally, wrap it all up with acing the interview. This top-down, structured approach is exactly what interviewers want to see. Section 1. The System Design Challenge. Let's start with the classic prompt that kicks off almost every data architecture interview.
Okay, let's dive right into this. The prompt is, design a reporting system that can answer, what were our top 10 revenue-generating products last quarter? Now, on the surface, that sounds incredibly simple, right? But that one single sentence hides an absolute mountain of architectural complexity. And how you navigate that complexity? Well, that reveals whether you truly understand data systems at massive scale.
So, picture this. You've got a production PostgreSQL database running your e-commerce platform. Orders are flowing in, everything's smooth. Then your CEO opens a dashboard, probably at 4 p.m. on a Friday, and asks to see total revenue by product category compared to last year, filtered by customer segment. Boom. Suddenly, your production database is literally on its knees. Standard transactional databases absolutely fail under these heavy analytical workloads. They just aren't built for it. Section 2. The Great OLAP Divide. To solve this Friday afternoon crisis, we need to go back to first principles. We need to understand the physical reality of how data is stored. There's a fundamental divide between OLTP, online transaction processing, and OLAP, online analytical processing. OLTP systems, like your Postgres database, optimized for small, super frequent reads and writes just to record transactions. They use row-oriented storage. But OLAP systems, think Snowflake or BigQuery, they are built to analyze history. They handle these massive, complex, exploratory queries across millions or even billions of rows. And to actually pull that off, they rely on column-oriented storage and denormalized schemas.
Now, here is where you can really impress in an interview. You need to explain why OLAP is so much faster. Imagine a table with 1 billion rows and 100 columns. If an analyst queries just 2 of those columns, say product category and revenue, a row-oriented database still has to read all 100 columns off the disk. You are literally reading 98 columns of data that you're just going to throw away. But an OLAP column store, it only reads the 2 required columns. You're doing 98% less input-output. Plus, because data in a single column is highly similar, it compresses dramatically better. That right there is the difference between a query taking 45 minutes and taking 4 seconds.
Section 3. Mastering the Star Schema. So we know how data is physically stored. Let's talk about how we model it logically. Enter the Star Schema. You see, business users don't think in normalized, fragmented database tables. They think in events and context. The Star Schema maps perfectly to this. At the center, you have your fact table. This captures what happened and how much. Surrounding it like a star are your dimension tables, which give you all the juicy context. The who, what, where, and when. The absolute, unequivocally most critical concept here is setting the grain of the fact table. This means defining exactly what one single row represents. Is it 1 row per individual ride? 1 row per daily summary? Every single measure must be true at that specific grain. Let's use a ride-sharing company as a quick example. To connect the context to the facts, you need keys. Now, a huge rookie mistake is using natural business keys, like a driver's email directly from the production database. No way. Instead, you must use surrogate keys. These are just sequentially generated integers. They're smaller, they join way faster, and most importantly, they totally insulate your analytical warehouse from any weird changes in your upstream source systems. And that brings us to a massive, massive positive interview signal: slowly changing dimensions, or SCDs. What happens if an Uber driver upgrades their vehicle from a standard Uber X to an Uber XL? Well, if you just overwrite their old record, which is SCD Type 1, you lose all that history. Suddenly, all their rides from last year look like they happened in an Uber XL. That's bad data. Instead, we use SCD Type 2. We add a completely new row for that driver with a brand new surrogate key and effective dates. Historical rides point to the old row, new rides point to the new row. Explaining this proves you care about analytical correctness, not just operational correctness. Section 4, the Medallion data pipeline. Let's move on and see how this actually builds into the physical pipeline itself. This is the Medallion Architecture. It's the dominant pattern used by tech giants like Databricks, Uber, and Netflix. Think of it as a physical pipeline for refining your data. Data lands in the brands layer exactly as it came from the source. It's raw, it's untouched, it's your permanent audit trail. Next, we refine it into the silver layer. Here, it gets cleaned up, deduplicated, and any sensitive PII, personally identifiable information, gets masked. Finally, it's modeled into the gold layer. This is the promised land where your fully transformed Star Schema lives, perfectly optimized and ready for your business analysts to query. But wait, how does data even get to that bronze layer in the first place? Well, you've got three main ingestion patterns. Batch ingestion pulls data on a set schedule. Change data capture, or CDC, acts like a live feed, streaming every single insert, update, or delete straight from your operational database's transaction log. And then event streaming captures application events in real time. What's really fascinating is that at immense scales, like Uber handling 15 million daily trips, companies don't just pick one. They use a hybrid of all three. Critical financial metrics might use CDC, historical logs use batch, and real-time fraud detection uses streaming. Section 5. Choosing the right tools. We have the architecture down. Now we need the tech.
As an architect, you can't just list off tools. You have to evaluate the trade-offs. Let's break down the transformation decision. You have to choose based on your team's skills and your latency requirements. If your team is packed with SQL-literate analysts, dbt is an undisputed game changer. It runs transformations directly inside your warehouse. If you're building a bronze to silver layer on AWS S3 and your team writes Python, AWS Glue is fantastic. Or maybe you want a managed Spark lakehouse, so you go with Databricks. But what if you need to process events with strict sub-millisecond latency? Then you're looking at something like Apache Flink.
Now, I need to give you a serious word of caution when choosing those tools. There is something called the streaming tax. Listen to this. Streaming architectures are literally 3 to 5 times more complex than batch architectures. You have to manage watermarks, late-arriving data, state management, the whole shebang. Please do not over-engineer your system. Running a daily or hourly batch process serves 95% of business needs perfectly well. Default to batch and only pay that streaming tax for specific high-value use cases.
Finally, your transformation layer pumps out that beautiful gold schema, and you need a serving engine to actually query it. Snowflake is incredible because it offers multi-cluster virtual warehouses. This means your data science team and your finance team can query the exact same data simultaneously without fighting for compute power. BigQuery takes a different route with a completely serverless Dremel engine. You just write SQL, and Google dynamically spins up thousands of parallel workers behind the scenes. And if you have a read-heavy workload that absolutely demands blazing fast sub-second latency, ClickHouse uses vectorized execution to process billions of rows per second.
Section 6. Acing the interview. We've covered all the components. Now let's synthesize this into the ultimate payoff.
Interviewers are looking for a very specific, mature response, and it breaks down into this 5-layer strategy. Do not jump straight into saying, oh, I would use Snowflake. That's a total rookie mistake. Instead, spend your first few minutes purely on layers 1 and 2. Clarify the workload. Is it read-heavy? What is the actual latency tolerance? Understand the access patterns. How are the users going to slice and dice this data? Only after you've totally defined the problem space do you move on to your storage, your transformation layer, and finally your OLAP serving engine.
There is a golden rule in system design. The engineer who explains why always outperforms the one who just names tools. The interviewer isn't looking for some theoretically flawless, perfect system. They want to see a candidate who thinks systematically, who articulates trade-offs with confidence, and who relies on core first principles to make their architectural choices. Which brings us to our final parting thought. The best architects don't just design great systems, they actively anticipate failure. So, if you had to go into work and implement this exact system design tomorrow, what is the very first architectural weakness you would proactively warn your engineering team about? Think critically about the trade-offs we've made today. Keep questioning, keep learning, and I'll catch you in the next explainer.